Session number is 24th today, and we are going to discuss the use of current mirrors in differential amplifiers. This discussion had already started. We wanted this REE to be replaced by a current mirror because we could not use REE indefinitely in a lumped form because of two difficulties. One is difficulty of fabrication in integrated circuit, and the other is difficulty of increasing what? Supply voltage. The third difficulty, accompanying difficulty, is that if you increase the supply voltage, if you increase the resistance, then there would be consequent increase of dissipation also, and integrated circuits are not geared to dissipate a large amount of heat. So the circuit that we had proposed was the following. The simple current mirror, capital R, let me draw this circuit again. This was Q2, this is the reference transistor, and then we have the second transistor where we want the current, and this resistance was RE. In the actual circuit of the differential amplifier, this is to go to minus VEE, and this is to go to plus VCC, and this is the current that I want. We call this I sub C1. This will actually be I sub, in the differential amplifier it would be I sub EE, okay, I sub EE. Now this transistor is Q1, and our interest was to find out what is the effective resistance, effective REE offered by this transistor current mirror. We wanted to calculate this, and in the process we had taken some numerical values to illustrate the values, and this we shall require now. VCC was taken as 15, VEE was taken as 0. The current through the reference current was taken as 1.43 milliampere, which means that this resistance is equal to 10K. 15 minus 0.7 divided by 10K is 1.43 milliampere. I sub C1 we want it to be 50 microampere as an example. This is the level of current that is permitted in an integrated circuit differential amplifier. Then R sub E was calculated as 1.68 K with 50 microampere and 1.43 milliampere. RE was calculated as 1.6 K, and we had assumed that VA 12 was equal to 100 volt, and beta was assumed to be, I don't remember, maybe 100. We will see as we go ahead. 200? Alright, let's keep it at 100. I think we took it as 100. Beta was 100. Yeah. Okay, now we drew the equivalent circuit very carefully, and we saw that in the equivalent circuit the resistance that is offered by the left of the circuit was the parallel combination of R pi 2 and what else? Capital R, R pi 2, capital R, then R02 because from collector to emitter, and also that GM2 V pi 2 was equivalent to a resistance of 1 by GM2. This we had agreed to call R sub 1, small r sub 1, and we also argued that because IC1 is much less than IC2, R pi 1, which is proportional to, inversely proportional to IC1, must be very large compared to R pi 2, agreed, and therefore R1 is very small compared to R pi 1, and we could ignore it in the equivalent circuit. Is the logic clear? Because the R pi is inversely proportional to collector current, and the two collector currents are widely different, R pi 1 would be much larger compared to R pi 2, and R1 is smaller than R pi 2 because it's paralleled by a number of other resistors, and therefore the simplified equivalent circuit would be like this. We have E1 C1, between E1 and C1 we have GM1 V pi 1 and the inevitable R01. Now we cannot ignore R01 because that is what we are going to calculate, the effective output resistance offered. Okay. Then from C1, well, it is between C1 and the resistance is between C1 and what? Which terminal? E2. Between C1 and E2, between these 2 points, what is the effective resistance? So this is E2 and this is the impedance that we want to calculate. Between E1 and E2, E2 is the same as, no, between, I beg your pardon, this is not E1. Yeah, this is E1, C1 to E1. Between E1 and E2, between E1 and ground, there is a resistance of R. Okay, and in addition, from E1, R pi 1, because we have ignored R1. R1 is much less compared to R pi 1, and the potential difference is, which terminal is positive, lower one or upper one? Lower one. That's it. Okay, this is the equivalent circuit by ignoring R1. And to be able to calculate the effective impedance, what we do is we connect a voltage source V and find the current I. You see, the expression can almost be obtained by inspection. As you can see, I is equal to, this current I is the same as the current flowing through this parallel combination, and this is minus V pi 1, minus because the polarity is this, divided by R pi 1 parallel RE. And if we write the KVL, V would be equal to the drop in R01 plus the drop in RE parallel R pi. Therefore, V is I minus GM1 V pi 1, this is the current through R01, multiplied by R01, then minus V pi 1. Is that okay? The drop in this plus the drop in this, which is minus V pi 1. Therefore, you can eliminate V pi 1 from these two equations and obtain the value of effective R0. Effective R0, which is equal to V by I. A bit of algebra will give you the following expression: R01 plus R pi 1 parallel RE multiplied by 1 plus GM1 R01. This is what we get. Now one should notice that R pi 1 would be very large compared to RE. RE is only 1.68 K. What is R pi 1? R pi 1 is beta by GM. Beta by GM. So beta by GM. What is GM? IC1 was assumed as 50 microampere divided by, let's say, 25 millivolt. This becomes 2 times 10 to the minus 3 mho. So beta is 100 divided by 2 times 10 to the minus 3 ohms, that is equal to 50 K. Agreed? So R pi 1, and what is RE? For the numerical example, it was 1.68 K. Therefore, R pi 1 is much greater than RE, which means that this quantity is approximately equal to RE. Okay. Now GM1 is this, What is R01? R01 is VA, which is 100 volt, divided by I sub C1, which is 50 microampere. So this is equal to 2 meg. Okay, 2 times 10 to the 6. Therefore, GM1 R01 is very large compared to unity. In other words, this term can be ignored. Agreed? From a practical example, this term 1 can be ignored. And therefore, my expression simplifies to a very simple one. And this is what is used for design. R0 becomes equal to R01, 1 plus approximately GM1 RE. Let's take the the values that we have got now. If we calculate the values, this is 2 meg R01, we already calculated. 1 plus GM1 is 2 times 10 to the minus 3 multiplied by RE is 1.68 multiplied by 10 to the 3. That means this is equal to 2 times 1 plus, how much is this? 3.26, agreed? So many meg. 3.36. How could I make that mistake? Okay. So it is 4.36 multiplied by 2, 8.72 meg. Meg. Now, you see the advantage of using a current source. By using two transistors, identical transistors, which is of no concern in an integrated circuit, because you make thousands on a chip. There is no problem in making 2 extra transistors, and the resistors that you require, one of them was 10K and the other is 1.68K, which are both manageable within the precincts of integrated circuit. With that, the effective REE that you have got is 8.72 meg, and therefore CMRR would be twice GM RE. GM is 2 times 10 to the minus 3 multiplied by 8.72 times 10 to the 6. So how much does this become? Greater than 32,000. Okay, a very large CMRR, and this is why.
So
and
GM is the which transistor?
Okay, it's a good point. Actually, I have this has been used strongly. The actual value should be how much? Half of this. Why?
The current is coming from both
Because IC1 is IEE, and therefore each transistor has half of this current. Each main transistor in the differential amplifier is half. Therefore, it would be 1 times 10 to the minus 3, and this would be 16,000. Even then, the figure is very large. I'm glad you pointed it out.
Sir, could you please show the equivalent circuit once again?
Equivalent circuit once again. I'll show you twice. All right. The question.
You have calculated connected R1 between E2 and E1. How have you done that?
That's right. R pi 1, I have to go back to the R pi 1 is between E2, this is E2, and E1. R pi 1 is from this point to this point, right, from base to emitter.
And so we have neglected I1.
Neglected, you see this resistance, the resistance looking here was approximately 0. Compared to R pi 1, this was negligible, and therefore it connected to ground. Is that okay?
Yeah.
Now I want to briefly recall the circuit. How this, I feel lazy to draw this again. I have this drawn here. Is this coming on the monitor? No, it's not coming. Okay. All right. So our circuit, how RE is used is like this. VCC, we'll draw it quickly. R sub C, then we have the two main transistors Q1 and Q2. These are connected together. This is supposed to go to REE. Instead, what we do is we take it to a transistor, let's say Q4 RE. This goes to minus VEE. This is the main transistor of the current mirror, and this is that Widlar resistance RE. And then from here we have the second transistor, which we call Q3 now, base connected to collector, and this terminal comes to the reference resistor, which was capital R, 10K, the value that we used, and this goes to, where should this go to? This terminal. The bases are connected to the sources, RS, and whatever source, VS1 and VS2. You see, what I wanted to show you is how R sub E is used. This is the circuit, that is R sub E. Okay? This pink colored outline, that gives you the equivalent of R sub E. Now the next
Equivalent of R.
EE, REE. That is what was 8.72 meg in our example. Instead of that lumped resistance, we have replaced it by this current mirror circuit. Now, the next point that we address ourselves to is the question of gain, the differential gain and the common mode gain. You know the differential gain for a differential amplifier is minus GMRC. Now GM naturally would be a small quantity because the current is very small. Current is of the order of 50 microampere. GM, as we said, for this particular example was 2 times 10 to the minus 3 mho. And therefore, pardon me?
1 into 10 is
Okay, 1 into 10 to the minus 3. So if you want a gain of 1, then R sub C is required to be a K, 1 kilo. The maximum R sub C that you can use is 50 K. Even that will give you a gain of only 1. I'm sorry, 50. Agree? So, on the other hand, differential amplifiers are required to have a large gain. And therefore, we play the same trick. That is, we replace R sub C now by means of a current mirror. That is how the op-amp circuit is being gradually built up. That lumped resistor RE has already been replaced by a current mirror. Now we want to replace RC also by a current mirror, so that we can use a large effective resistance without increasing the burden on integrated circuit fabrication or on the power dissipation or on the power supply also. Okay? So we want to use, instead of R sub C, a current mirror. Now you must notice that A sub C, the common mode gain, is minus GMRC divided by 1 plus twice GM effective REE. Okay? So if we increase R sub C, it increases the common mode gain also. Okay? It increases the common mode gain, it increases the differential mode gain. But what we are interested in is the differential mode gain. We want it to be as large as possible. The CMRR is not affected thereby. If we increase R sub C, CMRR remains the same. CMRR we tackle by REE. Okay? And the gain, absolute levels of gain, either differential mode or common mode, we take care by increasing R sub C by using a current mirror. Well, such a load, if we have an amplifier whose load R sub C is replaced by a current mirror, obviously the load ceases to be passive. Okay? Because we are using a current mirror. The current mirror is an active circuit. So we say that differential amplifier has active load. Active load. That is, R sub C is replaced by an active circuit which is equivalent to a large resistance without causing any disturbance in the DC conditions. Okay, large resistance we require under incremental conditions. Okay, that is effective R sub C. Now, in order to be able to consider the use of an active load in a differential amplifier, let us first consider a very simple case, namely a simple common emitter amplifier Q1, let's say, that goes to minus VEE with an active load. We first consider a single stage CE amplifier with an active load. Okay, let us say the voltage here is V sub I. We are only showing the AC voltage. Okay, the biasing has to be done properly. What we want to do is, instead of R sub C, we want to use a current mirror. So what we want to do is, we have to have a transistor whose collector current would be the same as the current of Q1. Okay, now Q1 is an NPN transistor, so its collector current flows like this, and if it is to flow like this, then obviously this transistor cannot be NPN, it must be PNP. Okay, that's the first point we notice, and this will naturally go to plus VCC. This is the main transistor of the current mirror. We require an auxiliary transistor to set the reference. So what we do is, we connect this to another transistor. This must also be PNP, whose base and emitter, whose base and collector are connected together. Alright, then this collector must go to a power supply through a reference resistor R, let's call it R1. It must go, now it cannot go to plus VCC, it must go to minus VEE, to minus VEE. What do you do with the emitter here? It must be connected to ground, because VBE must be identical. Is the circuit clear? Is it? We don't use it. We may, if we require much lower current. Okay, but if the problem is not of establishing a current here, our main purpose is to use a high valued resistor, equivalent resistor. Can you guess, by simply looking at this circuit, can you guess what the equivalent load of Q1 is? What is the equivalent load of Q1? One would be R01. Okay, let me name these transistors, Q3 and Q2. One would be from C3 to E3, it would be R03 effective. Now, is that all? There would also come in parallel, no, not R02. This point is not connected here. No, R pi also will not have it. R01. Isn't that right? The load from here to ground,
R01 plus R02.
not plus, it will come in parallel. That is what observation is. Observation, not seeing. Observation from here to ground is R01, offered by Q1. From here to ground, VCC is also ground, R03. So the effective load would be R03 parallel R01. And this is obtained purely by inspection. I derived the circuit from common sense, why PNP and why this connection, and now common sense says that the effective load, that is R sub C, would be approximately equal to it. There will be other factors, but these two shall definitely be there. Yes.
So please explain again why PNP.
Oh, why PNP? Because the collector current of Q1 has to flow like this, and since our main transistor would be here, Q3 collector must flow a current like this. And you can. Okay, good point. We can invert the collector, we can replace the collector by emitter and emitter by collector. There is a problem there. What is the problem? No? No? collector area is much larger than the emitter area. In a fabrication of a transistor, since the collector causes the main dissipation, the area of semiconductor silicon area for collector is much larger than the emitter. Okay, and therefore this is the natural mode. And we shall have a problem if emitter and collector are interchanged. They are interchanged in some circuits where it's not very critical, but where it is critical, it is better to use a PNP and NPN. And as I said, NPN and PNP in the same chip is no problem, and they can be matched absolutely identically. Okay. Now this result that the effective load is R03 parallel R01 has been derived by inspection, by observation. Let us see if this is correct by drawing an exact equivalent circuit. We will see something very funny there, and that is why this equivalent circuit should be drawn with caution. We start from B1, base 1 of the transistor Q1. Okay, from B1 to, it is always a good practice to identify the terminal. From B1 to E1, from B1 to E1 you have the resistance R pi 1, and this voltage is VI, the AC voltage. This is VI. Then you have GM1 V pi 1. Okay, this terminal is C1 collector 1 as well as collector 3. Agreed? So this is C1 and C3. From C1 to E1 we shall have the resistance R01, and from C3 to E3, which is the same as ground, from C3 to E3, you must do this very carefully. From C3 to E3, E3 is also grounded, and therefore it's the same point, we have R03. In addition, from C3 to E3, we should have the current generator, what? GM3 times V pi 3, which we have not yet identified, GM3 V pi 3. Okay, then we go to B2 and B3. B2 and B3 are tied together, connected together. So from B2 and B3 to E3 there shall be R pi 3, and this voltage would be V pi 3 with this polarity. What else should we have between B2, 3 and E3? What else?
R pi 2.
We should have R pi 2. Let me connect this so that I don't forget. Okay, and I have brought, I don't have space here, so I have brought it here down. Okay, now I am also trying to do something intentionally, confuse you. Do not be confused. Okay, R pi 2. What else do I have here? I shall have, because B2 is connected to C2, B23 is also the same as C2. So from C2 to E2, this is also E2. We shall have this current generator GM2 times V pi 2 is the same as V pi 3. Agreed? So we have GM2 V pi 3. There is a reason why I am writing this. What else do I have?
This is short.
No. From C2 to ground we have two other resistors. Can you name them?
R02.
One is
R02.
R02 and the other is
R1.
R1. That is absolutely wonderful. Okay. Now once again the point of observation or inspection. You look at this circuit, R pi 3 parallel R pi 2, GM2 V pi 3, R02 R1. What is the voltage across this? Voltage across this current generator? V pi 3. and therefore this current generator is equivalent to a resistance 1 over GM2. What is the voltage V pi 3 then? 1, 2, 3, 4, 5 dumb resistors connected in parallel, no source. So V pi 3 is identically equal to 0, which means that this current generator also goes off. Why is it 0? We have R pi 3, R pi 2, 1 by GM2, R02, R1, 5, I gave the adjective of dumb, they are passive. 5 passive resistors are in parallel, no source. What can be the voltage across this? 0. If V pi 3 is 0, then this current generator goes off, and therefore what is the output impedance of this between C1 and E3? What would be the output impedance? If I look at here, it is simply R01 parallel R03, because Vi equal to 0 will mean V pi 1 equal to 0. So the equivalent load that Q1 faces, it is a simple CE amplifier with active load. Equivalent load is R03 parallel R01. So R0 is equal to R03 parallel R01. Okay, which means 1 over R0 equal to 1 over R03 plus 1 over R01. Agreed? Now what is R0? R03, it is VA3 divided by I sub C3. Agree? I have to go back to this circuit. What is the relationship between IC1 and IC3? They are identical. Okay? Therefore, I can write this as I sub C divided by VA3 plus I sub C, where I sub C is IC1 or IC3. Is that okay? IC1 and IC3. That's correct. Because they are in series, the same current flows. So it is I sub C divided by VA1. That is equal to I sub C. Notice something very interesting that is coming up. VA3 plus VA1 divided by VA3 VA1. It is as if two voltages are connected in parallel. Okay? Alright? Now, therefore R0 is equal to VA3 VA1 divided by VA3 plus VA1 divided by I sub C. Therefore, the gain A sub D would be minus GM times this load, okay, minus GM times R0. What is GM? GM is I sub C divided by VT, 26 millivolt. Let's use it as VT for a moment. Then this multiplies R0, which is VA1 VA3 divided by VA1 plus VA3 divided by I sub C, and you notice that I sub C cancels. The gain therefore is simply given in terms of 3 voltages, which are internal properties of the transistor. Therefore the gain has become independent of external resistors. Okay? It is independent of VCC, VEE, R and so on. It is simply determined by minus VA1 VA3 divided by VA1 plus VA3 multiplied by VT. Gain has become independent of I sub C. So even if there is a small change of I sub C due to some other reason, it does not affect the gain. The gain has been stabilized, provided the early voltages, the thermal voltage of course depends on capital T. Okay, so the gain is now determined if it's a constant temperature enclosure, as is the case in most of the equipment that are used. Well, the A sub D becomes independent of all other conditions in the circuit, okay, except for temperature. Now, let's take a simple example. For the example that we have been using, VA1 equal to VA3, let's say 100 volt, and suppose VT equal to 25 millivolt. I want to calculate this in an easy manner. Then A sub D becomes minus 100 times 100 divided by 200 multiplied by 25.
Into 10
So
power
many?
3. Into 10 power 3.
Into 10 to the power 3, which means 2, so this is minus 2000. Alright? If the collector current is 1 milliampere, if the collector current is 1 milliampere, then what is GM? 1 by 25. So if I had used a lumped resistance, if I had used a lumped resistance R sub C minus 1 over 25, and if this gain is minus 2000, what is R sub C? Required how much? 50K. So what can be achieved by a 50K resistance? I am achieving by 2 transistors and a resistance. I have a resistance R1. Now where does this resistance show its teeth? Because the gain is independent of R1. What does the resistance do? That sets what? The reference current, IR. Don't you see that? I'll just show this. The circuit. Here. This current, IR, which will be approximately the same as IC2, IC3 or IC1. Agree? So this resistance sets the collector current, and what we could achieve by a 50K resistor, we have achieved by using 2 resistors, 2 transistors and 1 resistor. Yes.
Sir, if the final gain is independent of IC at all, then whatever may be the value of your IREF, how does it matter?
How does it matter? You have to set a Q point.
Okay, so that means the value of resistance is basically used for setting the Q point.
That
not
is correct.
IC.
That is correct. Q point means I sub C. Okay. This is one of the peculiar examples of a case where it was an elaborate equivalent circuit, but it simplified into a very small equivalent circuit. Is that clear? Because V pi 3 was equal to 0. And one has to be able to see it. Now, what I will do is I shall draw a circuit which is very commonly used, a circuit of a differential amplifier with active load, which is very commonly used. But in order not to complicate this circuit, I shall show REE as a lumped resistance. Okay. Otherwise, I will have to draw REE also, and this size of the paper would not contain it. So I will show it as REE. We have 2 main transistors, Q1 and Q2. This is differential amplifier with active load. Okay, we have the 2 bases. I want to show the base connections. I will show this, as I had promised, as a lumped resistance. Actually, this is also a current mirror. You can include this minus VEE, and this current is I sub EE. Let me show the input. The input is applied between the 2 bases. This is VD. Now, the current mirror comes like this, the active load. You see, we have 2 transistors, Q1 and Q2. Naturally, if a single common emitter amplifier requires 2 transistors for an active load, this should require 4. But people are very clever, circuit designers. They did with 2 and see how this connection is made. The 2 transistors in a current mirror circuit, because the currents are identical, that can be used for Q1 as well as Q2. So what one does is the following. This is a PNP transistor, and This is a PNP transistor. We call this Q4 and Q3. The reference transistor is now this one. The two bases are to be connected. This collector is connected to this base, and the two emitters are now connected to plus VCC. So this is a single current mirror. Agreed? Problem. What is the problem? Who sets the reference for this current mirror? This I sub EE sets the reference. The two collector currents are IEE by 2. So as long as this is constant, as long as IEE is a current source, which we achieve by using another current mirror, and in that current mirror IEE is determined by a reference resistor. Okay, so ultimately it goes back to a resistor, but one reference resistor is enough for setting the reference values for Q3, Q4 and also Q5, Q6, which is used for REE. Is the point clear?
No, sir.
So, no? You see, for a current mirror we require a reference resistor. Reference resistor would have been needed if this was referred to a resistance and a source. We don't require it here because IEE is again itself a current source, and therefore IEE can act as a reference for Q3, Q4 current mirror. The collector current here would be simply IEE by 2. So if IEE is referenced, then so is the Q3, Q4 current mirror. The current for this circuit is IEE by 2. Okay. The other thing, the output now is taken, single-ended output is taken from this. That is V0. Can you tell me why? Can you tell me why? This is the reference transistor, and therefore the output impedance is offered from this point to this point. Okay. The effective load of Q2 is this R04 in parallel with R0 2 or 3? 2. Now not 3. 3 is the reference transistor. Therefore the output is taken from here. Alright. This is the circuit of a commonly used 741 or 5039 or whatever type, or 701, whatever type you take. This is how the active load is used. One can argue, the question has not arisen yet, I will raise the question and answer it myself. The question is, are these two, are Q1 and Q2 now in a balanced mode of operation? You see, Q2 is supplied by Q4 and Q1 is supplied by Q3, but the two transistors are not connected similarly. The base is not connected to the collector here. Does that make a difference?
No, sir. I see, sir.
Ultimately it doesn't, but that has to be found out by making an exact analysis, which I find it convenient to leave it as a problem. And the problem is the following for you. The first thing that I want you to show is that RL1, that is the effective load of Q1, effective load of Q1 is approximately equal to 1 by GM1. Show. Obviously the effective AC loads of Q1 and Q2 are not the same. This is approximately 1 by GM1 for Q1, and for Q2 approximately R02 parallel R04, and they are not identical. So the two gains are not identical, but still it does not matter. V0 acts as the output of a differential amplifier, and it has to be shown. The two AC loads are not identical. No longer they are RC. Okay. This is the first thing I want you to show, and the second thing is that V0 by VD, that is A sub D, is approximately equal to GM. Which GM? GM2. GM2 is, does it differ from? They are all identical. Q1, Q2, Q3, Q4, the collector currents are the same. So I am simply writing GM. GM multiplied by R02 parallel R04. This resistance is very high. This resistance is not that high. So the two loads are different. Also notice that there is no negative sign here. Can you guess why? All right, I also did that as a problem, and I want you to show that this is equal to, well, obviously this can be shown very easily, that it is VA2 VA4 divided by VA2 plus VA4 multiplied by VT, which is now independent of the collector currents and so on. Okay. Hint: in showing this, you do well to ignore R01. If you do that, the equivalent circuit will be simple and you will be able to find both these expressions. The end in many cases justifies the means. This ignoring of R01 ultimately will be justified by seeing that the effective load that Q1 sees is not R01 but 1 by GM1, which is a small quantity compared to R01, and therefore R01 ignoring is justified. Okay, take this problem seriously and try to work it out. We next consider a differential amplifier using FETs, field effect transistors. Okay, and we shall see that the analysis is slightly different because of the current voltage characteristics of FET. This satisfies I sub D versus VGS is a square law relationship. However, if we move through this jungle by clearing IDS, S and VGS and VP, we get very similar results. What I want to do now is simply to draw the circuit and continue its analysis tomorrow. The circuit, as you can very easily guess, is very similar. We have two transistors, Q1 and Q2, RS and VS, 2 VS1, two transistors in which the two sources S1 and S2 are connected together instead of two emitters. Then this point goes an ordinary circuit. It will ultimately be replaced by a current mirror, but a resistance which we shall now call as R sigma sigma. Instead of R EE, it is R sigma sigma, and this voltage is minus V. What should be subscripts? Capital S, capital S. Distinguish between this small s and capital S, or you can use sigma sigma. That's better, so that we don't confuse capital S and small s. After all, capital S should be distinguished from non-capitalists. Okay, Q1 and Q2, and then we have two resistances, R sub D and R sub D, the drain resistances. The two are connected together and goes to plus VDD. There is no confusion here. There is a confusion because the difference voltage we have used as, but there should be no confusion. We will use V capital D as the DC difference voltage and V small d as the AC difference voltage. So I have used a double subscript here. That's why there should be no confusion here either, VSS. But it would be a matter of discipline to write capital S and small s, and I strongly suggest that you write it like I sign my name. Okay, I always sign my name with an S like this. I'm not a capitalist. Okay. The two voltages are, how did we denote these voltages? V capital D1, okay, and V capital D2. There should be no confusion, and this voltage is VOD plus minus. This is the basic circuit, and if you know BJT, you know how to draw an FET circuit. The fact that FET operation is unipolar, that is only one kind of carriers, it's a majority carrier device, leads to a nonlinear relationship between I sub D, the drain current, and the gate to source voltage. Also, the gate to source voltage has a limitation. VDS has to be greater than VGS minus VP, absolute value. So if all those limitations are taken into account, we shall be able to show next time that A sub D is equal to minus GM. What do you expect? RT. We will be able to show that this is true. And once we have established this, the rest of the analysis is very similar, and therefore I will not continue the analysis. I will leave it to you. Not completely. Partially, I will illustrate this by numerical examples in the problem session. That's all for today.
Rolling is the process of producing different components by plastic deformation of work material by passing it between rotating rolls. The process is called longitudinal rolling if the forming rolls are rotating in the opposite directions and flow of work material is along the length of the job and perpendicular to the central line of the rolls. By this process, we can produce products like bars of different cross sections, steel for constructional work, flat products like plates and sheets of various thickness can also be produced by this process. Another version or type of rolling process is transverse rolling. Let us have a look at a transverse cold rolling machine. In this process, the forming rolls are rotating in the same direction and the flow of material is either radial or the flow of material is along the axis of the job, which is also parallel to the axis of the forming rolls. A large variety of products like pulleys of different sections, rollers for overhead cranes, cycle freewheel, BB cups, gear blanks, and gears can be easily produced by this process. This machine can roll circular discs of aluminium, mild steel, and alloy steel of varying thickness and diameters. The two forming rolls are mounted on the spindles running in the bearing housings of the two blocks, one on either side of the job, and these blocks are moving in the dovetail slides of the main bed. In this process there is less material wastage, higher production rate, and long tool life. Hence, it is much cheaper a process than any other conventional process. Nobody can deny that we can travel faster, much faster than ever before. But at what price? Increased air, land and noise pollution, increased casualties and accidents, rapid depletion of petroleum resources, automobiles are, in fact, now recognized as the chief contributors to atmospheric pollution throughout the world, emitting huge quantities of lead, oxides of sulfur and nitrogen, in addition to carbon monoxide and carbon dioxide. Road accidents also take a heavy toll. In India alone, about 40,000 people die every year, and over 1 million are injured, and these numbers are rapidly increasing year after year. And as is common knowledge, automobiles consume a major share of petroleum products. Consequently, this endowment of mankind, accumulated over millions of years, is getting so rapidly depleted that by the year 2000, we would be left with only 40% of the total stock available at the beginning of the 19th century. Another major achievement of technology is the phenomenal increase in the energy availability per person, thanks to huge thermal and nuclear power plants. But this glitter of power availability too hides a lot of litter. Superthermal power stations of today are responsible for enormous pollution of their surroundings. Hydroelectric power stations cause immense social and ecological degradation due to the formation of large lakes and flooding of vast areas of land. And the hazards of nuclear power have only recently been highlighted by the Chernobyl accident. No one can deny the remarkable achievement of modern medicines. Yet, it is also a fact that many of the modern drugs have serious side effects.